But for right now, I think it's time that we get going on the Pluto planet debate. And we're also going to talk about asteroid impacts and the techniques for finding other Earths and what we know about planets around other stars. And if we have enough time, we'll also chat about some of the recent data that's been observed from the surface of Mars dealing with the salty water that we have there. So hopefully we'll have time to get to that. But before then, we are going to go ahead and introduce ourselves. I'm Daniel Batcheldor. That's me in the middle there. Look how handsome we all are. I'm the head of the Physics and Space Sciences Department here at Florida Institute of Technology. And the two faculty members that have joined us this evening are Dr. Chava. He has expertise in impacts of meteors into planetary atmospheres, which is something that we'll be talking about later. And also Dr. Darren Ragazine. His expertise is in the dynamics of planets in systems where we have many, many planets around their stars. So that's how those planets interact with one another. And he also has expertise in the outer solar system, the very dark and cold regions of the outer solar system, including Pluto itself. So I'm the chap in the middle talking right now, and then Dr. Palatai and Dr. Ragazine are the two kind gentlemen that will be answering your questions in real time. So you should be able to wave your hands or raise your hands or something like that and ask questions of them as we go through. So what is it that we are going to talk about this evening? We've got three topics that we definitely want to get to, and then I mentioned, of course, that if there's time, we'll talk about the Martian surface. But to start with, we're going to talk about planets around other stars. We're going to discuss how we know that they are there and how we can figure out what the properties of those planets are, how far away they are from their star, how big they are, and potentially whether or not they could host life on them. We're also then going to move on to talk about Pluto itself, which is a very exciting topic right now. I'm sure most of you are aware that in July, the New Horizons spacecraft hurtled past Pluto, quickly taking lots and lots of fabulous pictures. That some of those are going to be presented to you this evening. And we're going to discuss what makes Pluto different to the major planets in our solar system and what makes Pluto the same to some of the planets in our solar system as well. And then bringing up the rear, we're going to talk about the effects of asteroids and comet impacts on planets, including Jupiter and our own planet itself, the Earth. Now, what we'd like to start off and do is get you a little bit engaged, because I'm sure sitting at home, you've got all these temptations around you. You may have your Facebook window open. You may be eating some dinner or something like that, but we're going to get you engaged straight away. And we're going to do that by taking a poll. So we're going to have a quick vote of the people that are online over the question. All right. Now, some of you who are a little bit younger may not be aware that Pluto has a little bit of controversy surrounding it, and that is whether or not it is a planet. So we're going to run a little poll right now. You're going to be able to answer yes or no on this poll, and we'll be able to show you the results from that. And all we want to simply ask you is whether or not you think Pluto is a planet. All right, so that poll is now open, and we'll give you a few seconds to put your answer in. Do you think Pluto is a planet? And then later, after we've gone through and talked about Pluto itself, we're going to ask that question again and see if you've changed your mind. All right. So the poll is still open. Have we got people voting? Looks that way. Yeah. Good. Keep voting. All right. So we'll be able to see those results now. So 56% of you think Pluto is not a planet, and 44% of you think Pluto is a planet. All right. So bear that in mind. Bear that in mind when we talk about Pluto later. We'll see if we can get some people to change their minds. It's always a good thing, right? Okay, before we start talking about Pluto, we're going to talk about planets around other stars, which is a very, very interesting topic, of course, because we really are very interested in whether or not there are planets like Earth around other star systems. So bear with us a moment. So you should be seeing right now two pictures, one of a drawing of a spacecraft, the Kepler spacecraft, and one of a graphic of a pretend planet passing in front of a pretend star. So imagine you are using a telescope and you are looking at a star, and all you see is a point of light on the sky. You can't see the planet, and you can't really see any details about the star at all, apart from its brightness and how its brightness varies as time goes on. So you can see in this graphic here that a planet, if it is aligned in precisely the right manner that we need for it to appear to pass in front of the light coming from the star, will actually block some of that light. And if we take very, very quick pictures of that star with a very, very high precision instrument, then we can actually detect the drop in light coming from that star as the planet passes in front of it. We call this the transit method. So planets in our own solar system do the same thing. We can sit on Earth and we can use a special telescope to look at the sun, and every now and again we will see Mercury transit in front of our own star, and Venus transit in front of our own star as well. This doesn't happen all the time because these planets have got slightly different alignments in our own solar system. But the same thing happens in our own solar system, and so we can actually see other stars where this happens as well. So in 2008, we launched a spacecraft, well, not we, NASA launched a spacecraft called Kepler, and we'll talk about Kepler in a moment, Kepler the person. And what this spacecraft did was it stared at a patch of sky with a huge camera. And here you can see the patch of sky that Kepler stared at. And all it did was stare and stare and stare at this patch of sky and look at the light coming from hundreds of thousands of stars that were picked out. And you can see here that we've got a picture of the constellation Cygnus, the swan. And you can also see the faint background of the Milky Way, our own galaxy as well. So it's slightly above the plane of the Milky Way towards the constellation Cygnus. So this spacecraft is not like the Hubble Space Telescope, which slews around all over the sky and gets data on galaxies and star-forming regions and the planets in our own solar system. But this Kepler spacecraft just stared at one patch of sky and monitored for 4 years the light coming from stars that it could see with its huge camera. So what does the data look like that comes from the Kepler spacecraft? Well, we're going to have the brightness of stars and how the brightness of those stars changes as a function of time. So as time goes on, we can see that there are going to be blips in what we call the light curve coming from these stars. And so you can see here that along the bottom axis, we've got the time in days, and along the axis going up and down, we've got the relative brightness. So when the star has a relative brightness of 1 or 100%, we know, or we think, that there's nothing blocking the light from that star. And when you see a dip, so you see all these spikes going down to even 99.7% or 99.8%. That is when something has blocked the light coming from that star. Now, this is one particular star in the Kepler field. So this is Kepler 11. It's a very imaginative name. Now, when we carefully look at this light curve, it might look like a mess right now, but we can very carefully look at the light curves and see, when we zoom in on these curves, that there are some very distinctive shapes in the way the light is changing coming from the star. Now, in this case, it turns out that we have a very complicated system. We have 6 planets in the Kepler 11 system. So for each one of these dips, we can see different shapes. We see some of them are really deep, some of them are really wide. And so this is telling us details about that planet that's in that system. Not only can we see how deep how much of the light is missing, the depth of this light curve, we can also see how long the light is blocked from the star, and we can see that signal repeating over and over and over again as the planets go around and complete one orbit of their star. And some other interesting things you can see is the colors in the light curves on the right panel corresponding to the colors of the dots in the left-hand panel. And sometimes you see them align. And this is a very interesting feature of planetary systems that we perhaps will talk a little bit more about later. So what about Kepler the person? There was a reason why the Kepler spacecraft was named after Johannes Kepler, who was still is a very famous astronomer who lived in the late 16th, early 17th century. And he is most well known in the astronomical community for finding out some very important things about the planets in our own solar system. Kepler was very lucky. He benefited from some very painstaking research done by some earlier astronomers that very carefully mapped the positions of our own planets in our own solar system as they went around their orbits. And what Kepler found was that instead of trying to make all of the planets have circular orbits around the sun, he said, well, why can't they be elliptical? So an ellipse is kind of like what an egg looks like, right? It's an off-center circle, a kind of a squashed circle. And everyone wanted planets to be orbiting in circles because a circle is a perfect thing. It's got an infinite number of orders of symmetry, and everybody likes a circle. It's perfect, right? The planets had to be following perfect orbits. Well, it turns out that not everything in nature is perfect, and the planets follow elliptical orbits. And that became known as Kepler's first law. So Kepler's first law simply says that planets follow elliptical orbits. Kepler also has a second law that basically says if a planet is really close to the star, then it's going to travel faster, and if it's very far away, it's going to travel slower. And that's a result of gravity. So as something approaches something else, it's going to accelerate due to the mutual gravity between those two bodies. So Isaac Newton came along later and actually improved on Kepler's work, and he improved specifically Kepler's third law. Now, Kepler's third law related the period of a planet, so that's how long it takes a planet to make a complete orbit of its star. So the period of the Earth is 1 year. Kepler was able to show that the period squared, so the period times itself, in years, was equal to the distance of that planet from the sun. All right, so in astronomy, we have a very fundamental unit called an astronomical unit. It is the average distance between the Earth and the sun, and it's essentially 150 million kilometers, or 93 million miles if you prefer. So the distance of the Earth from the sun is 1 astronomical unit, and the period of the Earth is 1 year. So in the case of the Earth, it's very obvious that the period squared would be equal to the average distance of the Earth from the Sun cubed, so the distance times itself again. Well, it turns out that the other planets in our solar system also followed this same law, Kepler's third law. But what's really interesting is that there's absolutely no reason why any other gravitationally bound set of bodies would not follow this law as well. The physics that we work out here on Earth is the physics that applies everywhere else in the universe. So what we see happening in our own solar system, the physics that we see in our own solar system, is also going to be applied to other solar systems. So in the light curves we saw before, we were able to determine the period of the planets by how often we saw the dip in the light curves. And that tells us how far away that planet is from its host star. So now we've got a way of looking at planets around other stars and determining how short or how long their years are, how long it takes them to make a complete orbit, and how far away they are from their star because of something worked out by an astronomer 400 years ago. So if we know how far away a planet is from its host star, we can figure out how warm that planet is going to be. Now for Earth, we're very lucky because we are far enough away from our own sun, our own star, for liquid water to be present on the surface. We're not so close that the water boils away, and we're not so far away that the water freezes, or also it can also evaporate as well. So we're lucky. We live in the habitable zone around our own star. And just for a point of reference, Venus is kind of around the inner edge of the habitable zone around our sun, but of course Venus is not habitable. And Mars is around about the outer edge of our own habitable zone. And we don't think, well, maybe there was some life, but we haven't found any evidence of life on Mars so far. So from the results from Kepler, we're able to determine a lot about the planets that we see around, the planets that we detect around other stars. Now Kepler, the spacecraft, not the scientist, was not just looking at one planetary system that we saw from the light curve from Kepler 11, where we saw 6 planets. It's looked at hundreds of thousands of stars and found light curves that show us there are thousands and thousands of planets around other stars. Now this is something that we had no idea about. We suspected, but we had no evidence for until around 1995. That's when we found evidence of the first planet around another star. And since then, we've built the Kepler spacecraft, and now we know of thousands and thousands of these planets. So now we can start to ask even more in-depth questions about exoplanets. And one of the interesting things that we find is that most of these planets are found in systems where there is more than one planet in that system. So what you are seeing here is a graphic made by Dr. Ragozin himself showing the number of Kepler systems that have more than one planet in them, or have more than one planet detected in them. Okay, so I'll talk about what I meant by that in a second. But we can see that there are 463 star systems observed by Kepler where 2 planets have been detected. There are 149 Kepler stars where 3 planets have been detected. Now the thing you have to watch out for here is that that doesn't mean that there are only going to be 2 planets in that system, or there's only going to be 3 planets in that system. It means that we only have evidence for 2 planets. So one way you can think about this is that if we were to observe our own solar system, so Mercury, Venus, Earth, Mars, Jupiter, we wouldn't necessarily be able to detect all of the planets we have in our own solar system. We're only able to detect the ones where they are aligned in their orbits such that the light gets blocked out as those planets go around their orbits. You may also know, of course, that the orbital period of our outer planets is very long. It can be over 10 years. So we'd have to wait a very long time, whereas the Earth goes around in 1 year. The other thing to notice from this plot is that where the legend is, where the picture that's telling you what the colors correspond to and how many planetary systems have got more than one planet detected in them, we're not really able to see the region where the Earth would be. So in this plot, we're actually showing planet radius in Earth radii, so 1 equals the Earth. And of course, there are 365 days in our year. So the Earth actually would be in the bottom right-hand corner of this plot. And we simply don't have much data or any data down there. So we're still in a position where we have so much to learn about planetary systems around other stars using this transit method and using all of the other methods that we have for detecting planets around other stars. There are several other methods, but this is the one that we presented today. So what does this mean? What does it mean now that we know there are thousands and thousands of planetary systems just in that tiny patch of sky observed by the Kepler field? Well, just have a look at this picture for a minute and see how many stars you can count. In this picture, we're seeing the center of our own galaxy, the Milky Way. So that wispy bulge in the middle of the image is us looking directly towards the center of our own galaxy, the bulge of stars towards the center of our own galaxy. At the center of our galaxy, there is a supermassive black hole that's 4 million times more massive than our sun, but we'll save that for a webinar later. But if you're just counting the stars in this image, you'll quite quickly get bored and realize that there are literally billions of stars in our own galaxy. And the Kepler field, remember, just looked at a tiny, tiny patch of the sky and found thousands of planets just in that tiny patch of sky. So it actually turns out that one of the most interesting, most major findings in astronomy ever has happened in the last 5 years because of the findings of the Kepler spacecraft. And that finding is that almost every star in our galaxy, in the universe, is going to have a planet around it. Planets are features of stellar systems. They are not unusual. It is not unusual that there are planets around our own star. That is normal. So we're going to do another poll now. Now that you know how many planets there are, we'd like you to answer yes or no. See if you're still there. See if you're looking at Facebook or listening to me. The question is, do you think there could be life on any of these other planets? 10 billion other planets within our solar system. So the poll is open now. So go ahead and vote. See what you think. We'll look at those results in a moment. Wow. You guys are pretty cool. I don't think you need to guess how many people have said yes. Have we got the results up? All right, well, for those of you that can't see the results, everybody thinks that there could be life on one or more of these planets. All of you. Very cool. I've been watching Star Trek. I like it. Okay. So now we're going to move on. We've talked about planets around other star systems. Let's move back to our own solar system. So planetary science was originally to do with planets in our own solar system. And then it's evolved to include all of the other stuff in our solar system, the comets, the asteroids, the Kuiper Belt objects. And it's also now including all of those other planets that we just talked about, all of the planets we now know about around other stars. But coming back to our own solar system brings us to our favorite, the most loved, perhaps, object in our own solar system, Pluto. So we had a poll earlier asking whether or not you think Pluto is a planet. And we saw that a small majority think that Pluto is a planet. Sorry, a small majority. Let me look at them again. Yes, most people, 55% of you or so, don't think Pluto is a planet. So for those of you that don't think Pluto is a planet, and those of you that do think Pluto is a planet, here is some of the evidence to help you either support your point of view or perhaps challenge your point of view. So it's worth pointing out that Pluto is much smaller than Mercury, the closest planet to the sun in our own system. It's also slightly smaller than our own moon. But Pluto itself has moons. So there's two bits of information there that are quite interesting. First, Pluto is really quite small when we compare it to the other planets in our solar system, and yet it has moons, like all but 2 of the other planets in our own solar system. So that's interesting. It's very icy, and one reason we know that is it's shiny. So it reflects a lot of light, which makes it a bit brighter than we may expect. So for a long time, a lot of people thought that Pluto was a lot bigger than it really is. And it's only since we worked out that it's covered in ice, and that's not the type of ice that you put in your drink necessarily, that we now know that the Pluto is a lot smaller. The other thing is that it has a really weird orbit, if it were a planet. The orbit is elliptical, so going back to Kepler's first law, it has a very elliptical orbit, which means it becomes quite close to the sun. Well, close for an object that in the outer solar system, it gets as close as 30 times as far away from the sun as the Earth, and can get as far as 50 times as far away from the sun as the Earth. So it can go from 30 astronomical units, 30 AU, out to 50 AU. So that's odd. We don't have any other planets that do that. And it's also got an orbit that is misaligned significantly with the rest of the planets in our own solar system. So the planets in our own solar system, they orbit around in essentially a disk shape that is slightly wobbly, but not too wobbly. But if you include Pluto, then Pluto's really wobbly, right? It's got a highly inclined orbit. So that's very different from a planet. So Pluto is a very interesting object, which means that we've pointed the Hubble Space Telescope at Pluto, and you can see on the right there the moons of Pluto itself, Pluto in the center, and the light coming from Pluto here has been blocked out a little bit so that you can see the faint other moons. The P4 and P5, they've got names now, and we'll talk about those names in a minute. So let's have a look at what Pluto looked like until recently. So at the top left, we can see what the Hubble Space Telescope sees when it looks at Pluto. We can also take what we know about our own moon and make it look like what we would see it like if it were at the distance of Pluto. So if we were to take our own moon, put it at the distance of Pluto and observe our own moon at the distance of Pluto with the Hubble Space Telescope, that's what it would look like on the top right. At the bottom left, we have what we thought Pluto looked like based on Hubble Space Telescope data. So at the top left, you can see that Hubble sees little patches of bright and dark coming from Pluto. And as Pluto rotates, you see different patches of light and dark, which means we could make up an image of what we thought Pluto looked like at this very low resolution. That is until the New Horizons spacecraft approached Pluto. And so in the bottom right, you are seeing an actual picture from the approach, taken on the approach of New Horizons towards Pluto. And you'll see that this is where people said they could see a heart on Pluto. Right? So you see on the bottom right there, a feature that looks like a heart. And everyone went, oh, it's got a heart. We love Pluto. Now, it's important to realize that the New Horizons mission is a technological marvel. It was launched almost a decade ago. It traveled 3 billion miles and arrived at its destination within 72 seconds of when we thought it was going to get there. So here is a good example of why it's important to push the boundaries of our knowledge. Because as we want to do that, we need to build more and more complicated instruments, more and more technologically advanced instruments. And now we as a species are capable of sending a spacecraft hurtling through space to hit a tiny, tiny spot on the sky with very, very high precision, both spatially and temporally. So it's in the right place at the right time. So let's have a look at some of the brand new data that has come back from the New Horizons spacecraft. What you're looking at now is a real picture that has been sent back from the New Horizons spacecraft now that it has hurtled past Pluto. So to get out to a distance of 30 or 40 AU, New Horizons was going really, really fast, which meant as it went by Pluto, all its attention had to be on taking data of Pluto, and it did the job very, very well. However, it's important to remember that New Horizons was launched 10 years ago, which means all of the technology on board is around about 10 to 15 years old. And if you remember, or if you can remember, what everyday technology was like 10 to 15 years ago, for example, we wouldn't have been able to have this webinar 10 to 15 years ago, you would realize that it's incredibly difficult to send data, this amount of data, very quickly. So we have to be very, very patient to receive this data coming back from New Horizons, but it is worth the wait. So I hope some of you who are watching have a very high resolution screen and a really good internet connection. But I would encourage you after this webinar is over to go and find this picture yourself so you can get the full resolution version of this picture and just see all of the detail coming from the New Horizons spacecraft as it zipped past Pluto itself. So let's look a little bit more closely at some of the features that we can see on the surface of Pluto. So here we go. This isn't a color picture. This is just in grayscale, and it allows us to see quite a few of the really interesting features that we saw. So the first thing that we see is glaciers. We see glaciers on the surface of Pluto. This is incredible. We see them on the surface of the Earth, and we've now seen them on the surface of Pluto. But these are not made of the same thing as the glaciers on Earth are. On Earth, glaciers are made from water ice. On Pluto, the surface temperature is minus 223 degrees centigrade, or minus 370 degrees Fahrenheit if you prefer Fahrenheit. This means that other things like nitrogen freeze as well as water. So nitrogen itself becomes liquid at minus 195 degrees Celsius, and it becomes solid at minus 210 degrees Celsius. So on Pluto, nitrogen is frozen solid. So on Pluto, everything is so cold that nitrogen behaves like the water glaciers on Earth behave. So we see those. So those glaciers are moving, which means that the surface of Pluto, where we have these moving glaciers, is new. It is being covered over by these glaciers, which means that if there were any craters that had impacted the surface of Pluto, which was something that we had expected to see before the New Horizons spacecraft, those craters would have been covered over by these glaciers, which is why we see this very smooth surface. And you might be able to pick out some of the flows, the directions of the flows of those glaciers on them as well. So at the ends of those glaciers, we see really spiky, sharp features. These are mountains, miles high, made of water ice. It is so cold on Pluto that water is so hard that it basically behaves like rock does on Earth. So the nitrogen glaciers, as they come up against these rocks of water, will flow around them and leave little islands. You might be able to pick out some of those islands in the smooth glacial region, nitrogen glacial region. And then they also butt up against these really sharp mountains. Now, of course, on Pluto, because it's so much smaller than the Earth, the gravity is a lot lower, which means you can have a lot higher and sharper mountains. So these are just absolutely fabulous observations that are going to supply scientists with lots and lots of data to keep doing their research for decades to come. So it's a really good time to become a planetary scientist. We've got all of this new data coming from planets around other stars, and we've got all of this new data coming from the very outer reaches of our own solar system. So let's now return to that question that we asked at the beginning, whether or not Pluto is a planet. So we have a little graphic here that's plotting the distance of various objects in our solar system against their mass. So in the up-down direction, we have the mass, and it's in a logarithmic scale. You don't need to worry about that. Stuff that's closer to the top is more massive than stuff that's closer to the bottom. And then along the left and right, we have the distance of that object from our own sun. And there is a dashed line that goes through this plot. And the dashed line is telling us the difference between a planet and something else. So if you are a dot in this plot above the dotted or dashed line, if you prefer, then you are an object that's big enough to either absorb or scatter away all of the other stuff that's around you as you go in your orbit around the sun. So if you are above that line, you are big enough to clean out all of the junk that was in our solar system. If you are below that line, then you're in a little bit of trouble. You haven't been able to do that. And so we don't yet have the names of the objects in this plot. So let's put those up right now. So here we go, same plot. And now you can see where the objects in our solar system fall on this plot. So you can see at the top there, the very top, we have Jupiter, then Saturn, then Neptune, then Uranus, Earth, Venus, Mars, and Mercury. And you can see that all of those objects fall way above that dotted line that makes the difference between a planet and something else. And below the line, we saw two clumps of spots before. One clump is for objects in our asteroid belt, and Ceres is the largest asteroid in the asteroid belt. So that's the collection of rock between Mars and Jupiter. And over on the right, you can see where Pluto is, and Eris, which is another object like Pluto. So both Pluto and Eris are objects that are in the Kuiper belt, which is a whole collection of rocks and icy bodies that are in the outer solar system. They are further out than Neptune, so you can also call them trans-Neptunian objects as well. So now we can re-ask that question. Is Pluto a planet? So now we'll go to the last poll we have, and we'll see if there's been any swing in the voting. So the poll's open. Oh, there's been a huge swing. Still voting. Here we go. Oh. Nearly there, nearly there, nearly there. There are some of you still holding on, not convinced. All right. Have we got those results? Okay, so now 22% of you still think that Pluto's a planet. You're holding on. You love Pluto. You want it to be a planet. I suspect you may be a little bit older and you went to school at the time when Pluto was still considered a planet. But now you've got all of the evidence that we have to show that Pluto, I'm afraid, is no longer classed as a planet. We call it a dwarf planet or a Kuiper belt object. All right. So now it's time to move on and talk quickly about Kepler's moons. Pluto's moons. So here is a look, almost to scale, of how Pluto is compared to Charon or Charon, or however you want to pronounce it, Charon. And you can see that there are also 4 other moons, tiny little dots at the top there. Now, what makes these moons interesting is that they have discrete orbits that are in 3, 4, 5, and 6 ratios. So it's very odd that the orbits of these moons are basically dancing around for us in a very organized way, and we have no idea why that is. So that's an open question for somebody to come along and solve. This is data from New Horizons as well of Pluto's largest moon, Charon or Charon, however you would prefer to pronounce it. One of the interesting things here is that there is a canyon that stretches across the center of Charon. You can see it stretching from the bottom left up to about the middle right, bigger than the Grand Canyon. And what's interesting is that Charon and Pluto are tidally locked to one another. That means the faces, they always show the same face to one another. So if you were standing on Pluto, you would never be able to see the other side of Charon. And if you were standing on Charon, you would only ever see one side of Pluto as well. Now, one of the interesting things about the potential formation mechanism of both the Earth and the Moon and Pluto and Charon is that we think that they were results of impact events, huge impact events that happened very early on in the history of the solar system. And so we're going to move on now to the other topic that we wanted to discuss, and that is asteroids and comets and their potential to impact other planets and our own planet. So what you're seeing here is a real image that has been collected by the European Space Agency's Rosetta mission. And part of the Rosetta mission was actually to put a lander called Philae on the surface of this comet. Now, this comet started off in the Kuiper belt, and it came into the inner solar system and got caught into an orbit that now has a period of around 6.5 years. And what you're seeing is an object around about 4 kilometers across. So this is what we think a Kuiper belt object would typically look like. And one of the things that New Horizons is going to go on and do is actually go and look at another Kuiper Belt object, and it'll be really interesting to see if New Horizons sends back data that looks like this comet that we have here, 67P. And you can go and try and pronounce the other two names of the discoverers yourself in your own time. So these are the types of objects that are coming in from the Kuiper Belt and can potentially impact other planets in our solar system and the Earth itself. How do we know that? We've seen it happen directly. In 1994, a comet called Schumacher-Levy 9 broke apart and crashed into Jupiter's atmosphere. And in 1994, we had the Hubble Space Telescope. In 1994, we had other missions on their way to Jupiter. And so we got fabulous data from the impact of all of the fragments of comet Schumacher-Levy 9. There are 20 so fragments. And the reason this comet broke apart is because of the gravity of Jupiter. As it got close to Jupiter, the gravity of Jupiter ripped it apart into about 20 pieces. And all of these pieces impacted into the Jovian atmosphere. And so what you're seeing on the left there is an impact event in basically temperature color, infrared. And you can also see the previous impact events as well. Not only in the infrared, which are the three other bright spots towards the right-hand edge of Jupiter, but we also saw them in high-resolution Hubble Space Telescope images of Jupiter as well. So you can see these scars in the image that's on the bottom right. These are scars in the Jovian atmosphere as a result of comet Schumacher-Levy 9 hitting this planet. And you can do a lot of very interesting science with the shape of these scars. It's kind of like the same effect you see when you drop a little drop of water into a pool. You see a splash and you see rings propagating or extending away from where the impact site was. So we can use the observations of the comet Schumacher-Levy 9 impact and reconstruct in computers what happens as these lumps of ice and rock impact not only Jupiter, but the other planets in our solar system, including Earth. Now, Earth is, as you're probably aware, a very different type of planet to Jupiter. Jupiter is what we call a gas giant. So it is basically a really fluffy planet. And so the comet Schumacher-Levy 9 hit the atmosphere of Jupiter and was stopped in the atmosphere. Now, Earth is a rocky planet. It is a terrestrial planet, which means it has a thin atmosphere, which means that large rocks can punch their way through the Earth's atmosphere and make it to the surface of the Earth. And we know this has occurred as well because we see the craters that are left behind by these impact events. And there's a very famous example, if you've ever had the pleasure of visiting northern Mexico, northern Arizona. Not only is the Grand Canyon there, but there's also Meteor Crater. But we can look very, very closely at the surface of the Earth and see that there's a history of impact events on the surface of the Earth, and some of them have been absolutely catastrophic. And one of the most famous examples of a major impactor hitting the surface of the Earth happened around about 66 million years ago. We can see through very careful mapping of the gravitational field of the Earth a huge impact crater on the Yucatan Peninsula in Mexico. And we can do a little bit of math and figure out that an object around 10 kilometers in diameter punched through the Earth's atmosphere and exploded on the surface. As a result of that, a huge amount of debris was ejected into the Earth's atmosphere, and that debris settled down all over the Earth and left a layer of asteroid-rich material. There's a very there's a thin layer that we can find all over the Earth where there's an unusual amount of iridium. Now, iridium is a heavy metal that should have sunk towards the center of the Earth as the Earth formed. So it's very unusual to find it on the surface of the Earth, especially in a very thin layer. So that tells us that there was a huge impact where all of the debris from that asteroid, well, not all of the debris, but a lot of that debris got redistributed around the Earth. And we can see that in the geological record. Not only do we see that layer in the geological record, we can also look at the fossil record. Below the layer of asteroid-rich material, we see dinosaur fossils. Above that layer, we don't see dinosaur fossils. So we know that this event was very likely responsible for the extinction of one of the most prolific species or collection of species in the history of the Earth. We've also seen recent impact events on the Earth, and in 2013, in February, we got really good data from a meteor that entered the Earth's atmosphere above Chelyabinsk, Russia. And one of the interesting things about this is that lots of people just happened to be filming it at the time. There's various social, political reasons for that. But what we saw was this fireball go through the Earth's atmosphere. And there was a huge number of injuries as a result of this, because as this rock came through the Earth's atmosphere, it essentially exploded. And as it decelerated, there were lots of sonic booms and shock waves that blew out a lot of glass, and people got injured. About 1,700 injuries were sustained from shattered glass, while everyone was looking out the window to see, whoa, what was that? Unfortunately, they did so before the shock wave hit them, broke all the windows, and gave them all these injuries. And one thing we experienced in Florida here as the shuttle was landing, as the shuttle was decelerating, there was this double sonic boom that we heard from the shuttle. And as this thing broke apart, this meteor broke apart in the Earth's atmosphere, we also heard all of the sonic booms from those pieces of the asteroid breaking apart. All right, so how often do these things hit our atmosphere? Well, we've got all of this data not only from our own planet itself, but also from other objects in our solar system, especially the moon. And we can make yet another plot, exciting plots, and show how big an impactor is against how often that impactor hits the Earth. And so you can see all of the data that we do have, and we can take that data and push it all the way to the top right-hand corner of this plot and see that every 100 days or so, an object of about 1 meter in diameter hits our Earth's atmosphere. Now, most of the times these don't get seen because, well, most of our planet is covered with water, and so those impacts happen above unpopulated regions. But we have to worry about those impacts that can be large enough to cause mass extinction. But don't worry, because we are living in a technological age where we do have the ability to not only spot these potentially dangerous near-Earth asteroids, but also visit them, land on them, and give them a gentle nudge so that they will miss the Earth as they come close to us. So really, we as a species have been able to change the future of our own planet because we are now technologically advanced enough in order to deflect any potentially catastrophic asteroids from hitting our own Earth. So we know that in the next 100 years, there's a very low probability that any major catastrophe would happen. And even if we knew that one was coming, we will be able to do something about it. All right. So we covered quite a lot. We covered planets around other solar systems. We saw that the Kepler spacecraft did a fabulous job of staring at a particular patch of sky for 4 years and collected all of this data coming from stars. And as planets passed in front of those stars, we saw the light curves, and those light curves told us about those planets, how fast they were going around their star, what their period was, and how far away they were from the star because of Kepler's third law. We've also seen a complete revolution in the amount of data that we now know regarding Pluto. Pluto is no longer classed as a planet. It is known as a dwarf planet, a Kuiper belt object, or a trans-Neptunian object. There are bigger and better, well, there are bigger, we won't say better yet, but there are bigger objects like Eris in the Kuiper belt than Pluto. And we've also seen that Pluto has an interesting moon system, much like the Earth, that is likely a result of a very massive impact between the two bodies very early on in the history of our solar system. And we finally talked about how asteroids and comets can impact both planetary atmospheres, planets like Jupiter, and Earth itself. But there's no need to be worried about the Earth impacts, because we should, if enough people panic, we'll get enough money to be able to divert these near-Earth asteroids. So, in conclusion, what I think we'd like you to walk away knowing is that planetary science is an absolutely fabulous area of research for the next generation of scientists. So if any of what we've talked about this evening interests you, then we encourage you to go and look at what it takes to become a planetary scientist. You've got plenty of data to be working on for the next decade at least. And not only is planetary science interesting, but it's absolutely key for understanding our origins, because as it turns out, if asteroids and comets are responsible for mass extinctions, they also could have brought water and complex organic molecules to the surface of the Earth as well. But we'll have to save that for another webinar, because we have run out of time. So thank you very much for your attention. As a reminder, you will be receiving a recording or a link to a recording of this webinar. So look out in your email over the next day. Look out for that link. And from myself, Dr. Ragazine, and Dr. Palatai Online, we really appreciate you joining us, and we hope to see you again in the future. Thank you.